good morning to you. We are now on to lecture 11 in the second module, doing the review of basic structural analysis. We are going to start displacement methods in this session. It's something new to all of you and something very different and very interesting compared to force methods. So this is covered in part 5 of the book on structural analysis. We had looked at this slide earlier. This compares broadly the difference between force and displacement methods. In force methods, we look at static indeterminacy. The unknowns are forces, which we refer to as redundants. In displacement methods, we refer to kinematic indeterminacy. Here the displacements are the primary unknowns, the degrees of freedom. We solve for these unknowns using compatibility equations in force methods and using equilibrium equations in displacement methods. And we cast the force displacement relations in a flexibility format in the force methods, and we do so in using a stiffness format in the displacement methods. There are many force methods, but we had looked in close detail at the method of consistent deformations and the theorem of least work. The column analogy method is an excellent manual method, but we are not covering it in this scope. And the flexibility matrix method is what we will look at in detail later. In the stiffness methods, the earliest method is the slope deflection method, followed by iterative solution procedures, the moment distribution method due to Hardy-Cross, and Carney's method due to Gasper-Carney, which is similar to moment distribution method. So we will not be covering Carney's method in this course, but the most generalized method is the stiffness matrix method, which we will look at in real detail in the next modules. Again, just to recall, kinematic indeterminacy refers to the degrees of freedom. You need to look only at the joints. In this truss, for example, you have 7 joints. It's a planar truss. Each joint has 2 degrees of freedom, which we can mark using coordinates as shown 1, 2, 3, 4 all the way 11, 14. It's important to note that these 14 displacements need have no interrelationship between them. They are really independent. But once you fix the displacement vector, then you also fix the elongations in the bars, okay? And that relationship, those sets of relationships between bar elongation and the displacements are referred to as compatibility relations. For this truss to be stable, you need to arrest some of these displacements, and in this case, for example, if it's simply supported, 3 of them at least we should arrest. So let's say D12, D13 and D14 we arrest, and usually while labeling them we put the arrested coordinates to the end of our labels. So we begin with the free displacements and we end with the arrested displacements. The arrested displacements are those where we know for sure that the deflections are 0. So there is nothing unknown about them, and the degree of kinematic indeterminacy refers to the unknown displacements. In this case it will be 11. It is defined as the total number of degrees of freedom or independent displacement coordinates at the various joints in a skeletal structure. So in other words, we are able to locate this structure in its deformed configuration with reference to its original configuration, and once you know that the joints are located in a certain manner, we can really interpolate and get the location of any point on that structure in any bar with reference to those joint locations. We also discussed that unlike truss elements, beam elements also have rotations in addition to translations. So you have 4 degrees of freedom for a beam element. the primary structure or the kinematically determinate structure would be one in which all those 4 displacements are arrested, which is what you get in a fixed beam with both ends fixed. In a cantilever, one end is fixed, at the other end you have 2 degrees of freedom, a translation and a rotation. In a continuous beam, in this example 2 span continuous beam with an overhang, you have 4 degrees of freedom. Nk stands for the degree of kinematic indeterminacy, 3 rotations and 1 translation. A plane frame element is a kind of a combination of a truss element and a beam element, so you have 6 degrees of freedom, 2 independent translations and 1 rotation at each end. For example, if you have that portal frame, single base, single storied, with the base fixed, the kinematic indeterminacy would be 6. It would reduce to 3 if you assume axial deformations to be negligible, because the columns won't increase in length and the beam would not also increase in length, which means that the left end of the beam and the right end of the beam will move by the same amount, and that degree of freedom is called the sway degree of freedom. So you have 2 rotational degrees and 1 translational degree. And similarly for the box frame shown here, you have 2 sway degrees of freedom and 4 rotational degrees of freedom. We have seen this picture earlier. Here you have a 4-storied 3-bay frame. The degree of static indeterminacy is 36 and kinematic is 48, but if you make the assumption, which we normally do, that axial deformations are negligible, then the translation degrees of freedom reduce to 4, 1 sway degree in each floor. That means the entire beam in any floor will move like a rigid body horizontally. So D17, D18, D19, D20 are the sway degrees of freedom, and every joint has a rotation. So you have 16 rotational degrees of freedom, 4 translation degrees of freedom, 20 unknown displacements. Now let us begin by asking this question: when would you choose to go in for the displacement method compared to the force method? Logically, what would be the answer?
Some kind of symmetry. Then we can reduce the number of.
You can take advantage of symmetry both in the force method and the displacement method, and you reduce the unknowns in both. So if you were to do manually, you will realize that you have to solve some simultaneous equations. How many equations? Depending on the degree of indeterminacy, and you know that the work involved in solving simultaneous equations increases enormously, non-linearly, with a function of the number of equations to solve, right. So obviously manually, for example, it is not convenient to solve for more than 3, is it not? Otherwise you have to use some elimination methods or use a software to invert a matrix, etc. Your calculator, for example, can happily solve up to 3 equations, and that is why manually we should not put in more effort than that. If it is more than that, go in for a computer, which is what we are going to learn soon. So how do you decide which method to go in for, displacement method or force method?
Less
work. So if the degree of indeterminacy is less, you will choose that method. Take this example. I have got a fairly complicated frame, but there is some symmetry both in the frame and in the loading. Which method would you go? How long would it take you to solve this by the force method that you know? Okay.
The indeterminacy is more.
How much is it?
But here it is only 1.
Okay, first let us take advantage of symmetry, right. So let us cut the beam at the center at C. The appropriate boundary condition is a guided roller support, because rotation there is 0, but it can deflect. What's a degree? So let us look at this reduced frame. Let us neglect axial deformations. Tell me what's the degree of static indeterminacy? If it's just a cantilever, it's determinate, right? So you got some extra reactions coming there. How many of them?
1, 2, 3, 4, 5, 6, 7.
7. Well, at that hinge support you have 2, at that guided roller support you have 2, you have a horizontal reaction also possible, and at the top you can have a vertical reaction 1, so that makes it 5. That makes it 5. What about the unknown rotations? At the fixed end A you do not have any unknowns, at D you have a, well, potentially a rotation and a translation, at C you have a translation, rotation is 0, so 2 plus 1 3, at B you have a rotation 4, and at O you have a rotation, O is also joint, so you have 5. Is it clear? Sorry?
At D, what all relation?
Only a rotation. At O and B only rotations, at D rotation and translation, at C translation. Clear? So you have 5. So it looks like they are competing, but actually that 5 reduces to 1. So you will find that this is a problem you can solve in 1 minute if you are very alert and you understand the beauty of looking at the displaced configuration. We will see this problem shortly. So in this we will first, before getting into solving problems the hard way, let us first get a broad introduction to displacement methods. So we should understand the meaning of stiffnesses. So take this example of a simply supported beam subject to an end moment m0. You can find a relationship between the rotations. You have a clockwise rotation at O and an anti-clockwise rotation at A. You can get a relationship between m0 and theta, right? You just have to use the conjugate beam method. Can you tell me that relationship? m0 is equal to, or theta is equal to m0 by, come on. Okay, so I want you to learn some things and never forget them. This is one of those things that you should have really totally understood. Let us say we have forgotten, okay. How do you start from scratch? Always go back to conjugate beam method. So in the conjugate beam method, what are the boundary conditions for a simply supported case? It is simply supported. Of course whether you put a roller or not, it does not really matter because we are ignoring actual movements. So what is the loading diagram on this, on the conjugate beam? Conjugate beam, what is the loading diagram? It is a curvature diagram. In this case it is a hogging curvature. So the curvature diagram is m by ei. What will it look like? It is a triangle, right? That is m0 divided by ei. Theta is nothing but the reaction you get on this conjugate beam diagram. So what is the total area? What is the total area? If this is L, half m0 L by ei. 2/3 of that goes here. How much? So this is theta. If this was A and O, this is theta at O. What is it equal to? m0 L by 3 ei. And it is enough to know that the reaction you get here will be half that, which is theta naught. Is it clear? Now I do not want a situation where you need to have difficulty in answering this question. Is this crystal clear to you? Okay. So this is a measure of stiffness, of rotational stiffness. When I take a simply supported beam, apply a moment at one end, the rotation will be given by m0 L by 3 ei. Good. And at the other end it will be m0 L by 6 ei. Here the far end is hinged. This is the bending moment diagram. This is what we derived. Let us say that the other end A is fixed against rotation. I am not going into the proof, you should know this easily. It is going to be more difficult to rotate if the other end is fixed, and you can prove that from 3 EI by L the stiffness goes to 4 EI by L, right. You can prove this and you get a moment at the fixed end which is half the moment that you applied. This can be proved, it is an indeterminate problem. That proof you can work out, we have done this several times. Is it clear? Can you see here that this part is sagging and this part is hogging? Where do you think this point of contraflex shall be located? If the ratio of this moment to this moment is 2:1, this point of contraflexure will be exactly at L by 3. Is it clear? So this picture also you should know and keep it in mind. If you want, you can prove it a couple of times to get it in your blood. So these two pictures are the starting point in displacement analysis of beams. They are not difficult to understand. Is it clear? I can reverse the direction of the moment from clockwise, I have to make it anti-clockwise, everything gets flipped over, that is all. But the stiffnesses do not change because we are assuming linear elastic behavior. Is this clear? Okay, this should be firmly in your mind. You can also draw the shear force diagram if you wish, but that is easy. But the stiffness measure, remember axial stiffness in a bar, in a truss element, what is axial stiffness? EA by L, because there we are relating axial force N with what? With elongation E, right. So N, the axial force is EA by L times elongation. When you talk about a beam, you do not talk about a force and a translation, you talk about a moment and a rotation. Is it clear? And there are many ways of describing it. This is one way. You apply a moment at one end, if your beam is stiffer it will be more difficult to rotate it. So the flexural rigidity of the beam comes in the numerator, that is EI, and the length of the beam comes in the denominator, and there is a constant which depends on the boundary conditions. If the far end is simply supported, it is hinged, then it is 3 EI by L, if the far end is fixed it is 4 EI by L. Clear? Okay. Let us take this one step further. Let us say the far end is a guided roller support. Okay. If the far end is a guided roller support, you will find that deflected shape, what does it remind you of? It looks like a cantilever, right? It looks like a cantilever, and for a cantilever the bending moment diagram will be constant when you subject to an end moment, so it is m0 all the way, and you can prove that the rotation is EI by L. Of the 3 beams shown in this slide, the last one is the least stiff, it is easiest to rotate that. So I want you to remember these 3 magic numbers: EI by L, 3 EI by L, 4 EI by L. They refer to the same beam, the only difference is the boundary condition is different at the far end. See, it is the same m0. In this beam, here you are not allowing any translation, and you are allowing free rotation. Here you are not allowing translation or rotation. Here you are allowing translation, but you are arresting rotation. Is it clear? So there are different degrees of stiffness, but these 3 numbers you remember, and this is pure bending, the last case, so you have a uniform bending moment diagram. So these 3 are worth remembering because you can take a lot of shortcuts if you can invoke this understanding. Traditionally you arrest all degrees of freedom in the displacement method and get your primary structure, but if you can modify those stiffnesses for these 3 cases, your degree of indeterminacy drastically reduces, and we want to take advantage of that. Now in the previous slide we deliberately applied a moment and we found the rotation. Now we look at the same problem in a different manner. Here you have a fixed beam, okay, both ends are fixed. This is supposed to be kinematically determinate because there is no rotation at either end, there is no translation at either end, and anywhere in the beam there is no movement. So this is ground zero, everything is known here. Now here we will apply a rotation at the left end and the rotation at the right end, and we assume that this is happening on its own. We call it a rotational slip, okay, the ground moved, the fixity rotated on its own. So here what do you think, will you get bending moments? Of course you will, of course you will, because the straight beam has become bent. And will they be what will be the bending moments you get at A in the first case? What do you think you will get a moment here? What is MA, MAB if you wish? Oh, no, no, no.
It's fixed, so 4EI by
4EI by L, does it not remind you of the previous figure? So you should realize that you get the same shapes we drew earlier. You get 4EI by L at one side, 2EI by L at the other side, and you get a shear force which is 6EI by L squared. Is it clear? This is another way of looking at the same problem. The main difference between this picture and the previous picture is, here somehow the beam is, the fixity is rotating on its own and you are getting the same bending moment distribution. So here the end forces developed, the moments and reactions vertical forces developed are reactions, whereas in the previous case they are actions. Do you understand the difference? But from a displacement method point of view, you do not care whether they are actions or reactions, you are looking only at the deflected shape because kinematics is your primary focus of interest. Does it make sense? So you should be comfortable with both approaches to stiffnesses. You can begin with a kinematically determinate structure like this, and you apply a unit rotation, and the moment that comes where you apply that unit rotation is a measure of stiffness. In this case it is clearly 4EI by L, but you also get what is called a carryover moment at the other end, which is half the moment here, which is 2EI by L, and both are clockwise. Now there is a sign convention traditionally followed that clockwise moment and clockwise rotations are positive. Now we will learn later how to change that sign convention, but in the introduction and for using slope deflection method and moment distribution method, we will stay with that convention. So far so good, you understood this? Now let us try to convert all those beams into an equivalent spring. Okay, so we have a rotational spring like a door spring, and you know the moment that you apply is linearly related to the rotation, right? So if you have the first case where you are fixing the left end, then you agree the stiffness, if you reduce this to a spring, the spring stiffness will be 4EI by L. If you take the next case where the deflected shape looks like that, you get 3EI by L. If you take the next shape where you have a cantilever type behavior, you get EI by L. Now you can also get the same EI by L by fixing the left end and applying the moment at the other end, right? So you have to look at the deflected shape. From the shape you figure out whether you got a cantilever behavior or not. Is it clear? And this can be proved. So 3 numbers to remember: EI by L, 3EI by L, 4EI by L. That is all you have to remember. With that knowledge you can crack many problems, reducing the degree of indeterminacy tremendously and doing things that were unthinkable in the force method. Let us demonstrate. I have got here 2 frames, 4 members each, rigidly connected at the center, at the joint O, and in the first case all the elements are simply supported at the extremities, in the second case they are all fixed. Now the question is, can you draw the bending moment diagram and the deflected shape? Please try it. In force methods it is not so easy, in displacement method it is pretty easy. Can you draw? What will they look like? Just draw. That m naught is going to be shared by those 4 elements in what proportion? Equally, because all 4 look identical. So will you do that? Just try it. It's not difficult. Yeah, so will the roller make a difference? You have to think. As far as rotational stiffness is concerned, 3EI/L does not depend on whether it is roller or hinged. As long as it gives you a reaction, it works. So it is not difficult. You must do this in 1 minute. That is all it takes. The deflected shape and the bending moment diagram drawn on the tension side. So until we reach matrix methods, I want you to get the intuitive understanding of structural analysis strong, because once you get into matrices, you are just doing numerical techniques, you will not get a physical feel. So the physical feel is something you need to nurture to really enjoy and master structural analysis. Right? So you agree the deflected shapes will look like this. In the left case, in this case, it freely rotates here and that rotation will be theta naught by 2. You agree all the 4 will have to rotate by the same clockwise angle of theta naught. Why? Because the joint is rigid, that is the correct answer. And here also it will rotate by something which I refer to as theta naught with a tilde. Which rotation will be more, the one on the right side or the left side? Left side, because this is stiffer. It is stiffer because here at all the other beam ends you are not permitting any rotation, you have a point of contraflexion in the middle. Now can you draw the bending moment diagram? Easy. So you can look at it as though it is a spring and the spring stiffness is K naught, spring stiffness is K naught. What is the value of K naught in the first case and what is the value of K naught in the second case? What is the K naught in the first case?
K naught is infinity.
3EI/L, that is for one beam. You have 4 of them. Divide by 4 or multiply by 4. Why multiply by 4?
M naught by 4 it is in, no sir. So
4 of the springs will be opposing the rotation, so we'll divide it by 4, so the stiffness.
What is K naught? Tell me. What is, supposing I replace that whole frame with a spring as I showed here. Tell me, give me an expression for K naught. Huh? So you are multiplying. In other words, do you agree that the stiffnesses of all the connecting members will add up? They will add up. Why will they add up? Because equilibrium demands that they add up. Okay. So let us say there are 4 elements. Do you agree that equilibrium demands that m naught will be the sum of all those 4 beam element ends, and for each of them you can say K1 naught into theta naught, K2 naught, etc. Agreed? So we said in structural analysis you should be sensitive to 3 things. One is equilibrium of forces and moments. Second is compatibility. Compatibility is what made you say that theta naught is common for all the 4 members. And the third thing is the force displacement relationship, which is where K naught comes into play. Is it clear? So we are invoking all 3. Now this is the reason why This is the reason why. You see, m1 naught is k1 naught into theta naught, m2 naught is k2 naught into theta naught, etc. And we said m naught is k naught into theta naught. This is why we say k naught is the sum of the individual element stiffnesses. This is a proof that the stiffnesses add up, that you find the stiffness, if all 4 are equal, find the stiffness of one beam element and multiply by 4, not divide by 4. It increases, it becomes stiffer. It is easier to rotate one element than to rotate all 4 simultaneously. You have to apply that much extra moment. So theta naught can be calculated in that manner, and in the first case it will be 4 times 3 ei by L, in the second case it will be 4 times 4 ei by L. So now you are comfortable with that. What about the bending moment diagrams? Drawn on the tension side. Did you draw it that way? How many of you in this class drew the bending moment diagrams correctly? What happened to the rest of you? Is this difficult? Tell me. Is this difficult to draw? M naught gets shared m naught by 4. It is a linear varying diagram. Okay, where is tension? It is clearly in the direction shown. The moment at the other end is 0. In the other case there is a carryover moment of m naught by 8. Does it make sense now? So I want you to slowly get into the groove and understand how powerful this method is. Now let us take this problem where you have a similar situation, but I have put a different boundary condition at all the 4 ends. Okay? This is the problem we referred to right in the beginning, and I asked you which is easier, force method or displacement method. Now we said that there are 5 unknown displacements. I will not go back to that. Let us say all 4 elements have the same length L and flexural rigidity EI. I am saying you can solve this problem in 1 minute, and that is wonderful if you can do that, right? Can you do it? Can you give it a shot? Okay, first thing you should try to do is draw the deflected shape. That will give you a clue. Draw the deflected shape. You really try it, because you have to move your brain. Draw the deflected shape. Very few people have really appreciated the power of the displacement method in this kind of intuitive way. There is a rotation theta naught common to all the 4 members. How will it rotate? You do one thing, first you draw a cross at O and draw the tangents, okay. Then you have to bring them back to the extremities in the appropriate manner, that is all. Have you done it? So I will reveal it to you. This is what it should look like, and an amazing thing you discover. What do you discover? I drew this cross and said everything rotates by theta naught, right? So this first beam must come back here, agreed? This must come back there, and you remember that if this is theta naught, this will be half theta naught, agreed? This will rotate theta naught this way, and you can prove that this deflection is related to theta naught, so it is theta naught L by 2. And this, there is no reaction here, so this is going to rotate like a rigid body. And if theta naught is small, this is theta naught into L. So what do you conclude? There are really no 5 independent rotations and translations. There is just one unknown theta naught, just one unknown, and so it is not difficult to do. So can you find the bending moments now? So these are problems with a single unknown rotation, and many difficult problems can be reduced to this level. So how do you think that moment 160 kilonewton meter be shared between elements 1, 2, 3 and 4? Which will take the largest? This is like giving a a project to a team of 4 students, okay, all will get the same total marks, which is the same rotation, but one will end up doing more work than the others, and there will be one guy who will just hang around and reap the benefit, like this element 4, which is not going to resist at all. The stiffer elements will attract more load, right? But they all get the same result because it's one team. That's what's happening here. You get so it's depicting a law of nature. So which is the stiffest among those 4? 1, 2, 3, 4. What is the stiffness of 1? 4 EI by L. Very good. Stiffness of 2? 3 EI by L. Stiffness of 3?
EI by L.
Stiffness of 4? 0. Now tell me what's the moment going to 1?
4, 3, 2, 1, 0.
Throw away EI by L. You got the ratios now. 4 is to
M naught by 2.
80.
naught by 2.
What goes to element 2? 60. What goes to element 3?
20.
Do you get any moments at the extreme ends? At A, do you get something? You get half of 80 in the same direction. Now can you please draw the bending moment diagram on your own? You got the answers intuitively. Draw it. So you can expect simple questions like this in your coming quiz. 1-minute answers, but you can take 10 minutes if you wish. But if you solve for 5 unknowns, it will take you 1 day. You draw it consistently on the tension side. So all that is something you have learnt by now. Okay. It's not difficult. I want all of you to master this. Everyone in this class should understand this and be able to do it correctly. Again, only when you look at the deflected shape you will know which is the tension side, otherwise you will be doing it wrongly, as I can see some of you do. Which is the tension side? Draw the deflected shape. Okay, so this is the first element, 4 EI by L. This is the second element, 3 EI by L. This is the third element, EI by L. And the fourth is not worth drawing, it's a straight line. These are the stiffnesses. This is the 160 kilonewton. Total stiffness adds up to 20 EI by L. And the ratio is 4:3:1. By the way, this is moment distribution. You are distributing that 160 to the 4 elements in that ratio, 4:3:1:0. You correctly said 80:60:20. And did you draw this? How many of you did it correct? Raise your hands. That's not okay, some of you did, but you should be able to do it. See, after you reach the goal post, you have to put the ball in. This is the finish. Okay, have you all understood? This is drawn on the tension side. I noticed you did it, but you didn't draw it on the right side. So it's clear. Remember there's a carryover moment. Remember that in OC it's a cantilever behavior, moment is constant. Does it make sense? So we are synthesizing all that we learned in this very class in the first few slides in this problem. Clear? And you got your answer. You know everything now. You know the complete displacement field, complete force field. You can also find the shear forces if you wish. We are skipping that. Now let's look at more interesting problems. Okay, you have solved the earlier problem. Can you solve this problem? Take advantage of symmetry. Can we cut it in the middle? Will it look like the problem we did earlier? Which will look like the problem we did earlier? The left one or the right one? With the left half or the right half? Right half, because when you cut it at A, first you draw the deflected shape here. Do you agree the deflected shape will look like that? Why will the slope be 0 at A? No. Argue it. Why is theta 0 always at the line of symmetry. We have to argue convincingly.
It is rigid and
Right. So the argument is, if it were not to be 0, it has to be either clockwise or anti-clockwise, and that would violate symmetry. That's the argument. Symmetry means on both sides you should have theta equal and opposite. If one is clockwise, the other should be anti-clockwise, then only you get a mirror image, right. So if both have to be equal, it's mandatory that the slope will be 0. Is it clear? So you can now take the right half, and this is the deflected shape, right. This is the deflected shape. No, remember we did this for the earlier problem. Now the only change is, there are some changes here. Well, we have deliberately flipped over B and D to make you think. Please note, it is not identical. This is the problem we solved. This is what we solved earlier. Remember, here this is a straight line, whereas here this is a straight line, because the roller support is here. It is a roller position in the wrong way. So what will this look like? Can you tell me? If you have to use the results we did already and draw for that, won't it look like this? So you must flip it over properly, right, and then you can add the other half, mirror image. So that is all it takes. 1 more minute for drawing the mirror image. If you are using a computer, it is very easy, it is cut and paste and rotate. Okay, done. Look at another one. What about this one? At C now, theta is 0, but it can translate. So now which half will look like the one we did earlier, left or right? Now it is the left, okay. So same logic, same logic. Now you do the left half and you add the right half. So you can take this to any level of complexity, but you see we built it up on very simple fundamentals. So you get many types of problems. The easiest is this type, single unknown rotation with a nodal joint moment, right, which you distribute depending on relative stiffness. You will find many problems can be reduced to this, but in real life, where do you get a concentrated moment acting? It is not very common. What is more common is intermediate loads. You will have a UDL or a concentrated load or a triangular load. So that is the next type of problems we look at, arbitrary intermediate non-nodal loading, but still only one unknown rotation. So we will proceed stage wise so you can master everything. What do you think is the next level of difficulty? More than one unknown rotation. Let us say continuous beam, you have 4 rotations, okay, you are right. What is the next level of difficulty? When in addition to rotations that are unknown, you have unknown translations, okay, unknown like the sway in a building, that is more complicated, right. So that is a 4th type. If you know how to do all these 4 types, you are the ustad, you know displacement method, and I want all of you to master it because it is not difficult, but you have to think, you have to use your right brain to intuitively understand and simplify the problem, and you have to use your left brain to solve the problem logically. Is it clear? It is a powerful way to build up your inner resources. So this is one of the great advantages of structural analysis, one of the few courses that you get to learn where you really master the subject. One of the students who dropped out of this course met me and he said, "Sir, I am finding it difficult because see, it is not coming naturally to me." There is an old Chinese saying that if you want to eat roast duck and you decide to eat roast duck by standing on a mountain top with your mouth open waiting for it to drop, you will have to wait for a very long time. You see, if you really want to develop your brain cells, nothing should be easy, so easy that you can naturally digest it. You get to the point of it becoming easy after you have done the inner work. Once you have done the inner work and you have developed your potential to that level, then one look in the answer and the roast duck will fall into your mouth, but not otherwise, not an untrained mind. So I want you to take this seriously. This particular course, especially displacement methods, properly understood, has an aesthetic charm also to it. So you have to really relish this problem. Did you like what we did till now?
Yes, sir.
Okay, so it's challenging. Okay, we get some nice aesthetic music also. So this is increased difficulty in solving, and please note that in the earlier problem also we had that guided fixed support swaying, but we bypassed it. We had also rotations at the simply supported ends, we bypassed that. So in many cases involving sway, it is possible to ignore the translational degrees of freedom and you reduce the degree of kinematic indeterminacy by using modified stiffness elements, modified element stiffnesses. So from 4 EI by L we went to 3 EI by L, went to EI by L, and modified fixed end moment. So if you take this technique, really you can solve difficult problems in a very short time. And let me tell you, manually it's really not worth doing any of these methods if your NK is more than 2, right? Then you use a software to do it, but it's foolish to use a software when you can do it in 1 minute manually. And I regret to say the vast majority of engineers coming out of engineering colleges worldwide will still need an elephant to drive in a small nail. So use the right technique at the right place, right? So we will just conclude by taking a look at the meaning of stiffness matrix. Here you see a 3-span continuous beam, right? How many degrees of freedom are there? 2 degrees of freedom, right? Theta B and theta C, there is no translation. Let us label those potential moments that can be applied there as F1 and F2. So D1 is theta B and D2 is theta C, all clockwise assumed positive. Is it clear? So D1 is theta B, D2 is theta C. Now the stiffness matrix is defined as F is equal to KD. So F1 is K11 into D1 plus K12 into D2, and F2 is K21 into D1 plus K22 into D2. I want you to tell me, can you generate this matrix from whatever little you have learned till now? Can you write an expression for K11, K21, K12, K22, physically understanding what is going on? You can do it. So the great advantage of knowing that stiffness matrix, which is a property of that structure, is if someone were to give you the displacements, which is very unlikely, you can find what forces caused it. But the more common problem is you have some unknown loads, you have some known loads F1 and F2, and you have to find D1 and D2, and from that knowledge of D1 and D2 you must draw the bending moment diagram. So that you can do if you invert this matrix. So how do you get K11 and K21, the first column in that matrix, stiffness matrix? Put D1 equal to 1 and D2 equal to 0, because that is the definition of the stiffness matrix. Will you draw a sketch? Will you draw a sketch of the deflected shape where D1 is 1 and D2 is 0? Just draw it. Just draw it. Will it not look like this? D1 is 1 and D2 is 0, right? Can you draw the bending moment diagram for this? Or even if you do not draw it, can you write an expression for K11 straight away? K11 will be the external moment you should have applied there to get this shape. So it will be the sum of the moments you get at B and BA and BC. What do you get in BA? 4 EI by L of that element 1. What do you get? Plus? Plus what? No, you are arresting. See, when you say D2 is 0, someone is holding it at C and preventing that rotation. So it will also be 4 EI, perfect. So, and if you take the other case, it will look like this, right? You are now allowing D2 but arresting D1. So if you draw the free bodies, they will look like this without those forces, and 4 EI by L and 4 EI by L, but for the second element with the carryover. And so do you agree K11 is 4 E I1 by L1 plus 4 E I2 by L2, clear? Very easy to do. What is K21? K21 is what you get at the support which you artificially fixed, right, F2. What will it be? 2 EI2 by L2, right? Similarly you can do for the other case, and you see the beautiful symmetry in K21 and K12. That is how easy it is. So it is not difficult once you know, once you are comfortable with the kinematic determinant structure. We will stop here, we will continue tomorrow. Thank you.